Let's start chapter 17. The first section is introducing us to buffer solution. We're going to see how buffers work and how pH changes in buffer happens after a strong acid or a strong base is added. So let's talk about the most common buffer that we know. If I were to drink a can of soda, do you think it's going to affect my body? The answer is no, mainly because the blood that flows through our body has a pH of 7.4 and it's a buffer. So if I were to drink a can of soda, my blood is not going to become low in pH. It's not going to suddenly become 2 or 4 or 1. Why is that? Because the buffer makes sure that there is no sudden changes in pH. So buffer solutions resist changes in pH by neutralizing the acid or the base that's added. And it's governed by something that is known as the common ion effect. Now, before I give you the definition of common ion effect, I'd like to show you an example of common ion effect so it will make much more sense. So here's a question: calculate the pH of an aqueous solution containing 0.30 molarity of HNO2. So let's stop at this point. Now, HNO2 is a weak acid. Now, we've been doing ice tables for the past 3 weeks. So when you see this, you should right away know what to do. So there is a weak acid. You do weak acid plus water gives your products and make an ice table for it. So for this ice table, the only initial amount given is 0.3 molarity, and everything else should be 0, and water should be nothing because it's liquid. So this is what you should have as an equation. So you should get used to having this as an equation. That's the very first step. Do you have this equation? As we are going through these examples, go ahead and write the ice table and solve it. That's the only way to get good at it. So your second line is going to be changed where the reactant is negative x and the products are positive x and positive x. And then finally equilibrium is 0.3 minus x and x and x. So we go ahead and put it in the Ka equation to get our hydronium ion as 0.013 molarity. Now if you have the hydronium ion, which was the X over here, that means you can find the pH. So remember this number 0.013 and the final pH is 1.89. Okay. Now we're going to go ahead and look at a solution containing 0.30 molarity of HNO2 and 0.20 molarity of NaNO2. Now, the only difference between part A and part B is we now have sodium nitrate added to this mixture. Now, carefully look at the two things we have. We have HNO2 and we have NaNO2. What is something about them that we have learned before? So you should recognize that this is an acid, a weak acid, and this is a conjugate base of a weak acid. So how do you get a conjugate base? If you take the hydrogen away, you have the conjugate base. So we actually have a combination of a weak acid and a conjugate base. So keep that in mind because that is important. So in this particular case, we are going to have an initial amount of 0.30 for the acid, and for the NO2, we are going to have 0.20. So again, we have the exact same equation, but the initial, we're going to have NO2 ion with an amount. So we're going to, just so that previously we did X, we're going to do Y, and then we're again going to do that Ka is equal to this times this divided by this. So we now have a hydronium ion as 0.00084. If you remember in the previous case, we had it as 0.013 and our pH was 1.89. So only because we had 0.20 molarity of nitrate ion added, the amount of hydronium went way down, and you're going to see that our pH also went way up. Why did this happen? So this again goes back to Le Chatelier's principle. In the previous example where we just had this acid, this was 0 initially. So in Le Chatelier's principle, the stress is on this equation, so it's actually going to go towards the product. In this particular example, we already have some product, so the reaction is actually going to go in the reverse direction, and we are not going to have the weak acid ionize and form hydronium ion anymore, which is why we see the pH is rising instead of decreasing. So what we find is that when we have a common ion, so anyways this ionizes into hydronium and nitrate ion, but if we add an addition nitrate ion, we see that it ionizes even less. So this is known as the common ion effect. So the acid is a weak acid, it produces small equilibrium concentrations, right? However, if you add the ion which it is producing, we see that the equilibrium shifts towards the reactants and it suppresses the ionization of the acid. This suppression of the ionization of a weak acid or a weak base is known as a common ion effect. And we see this in buffers a lot. So what's a buffer solution? So the example we saw right now was a weak acid with its conjugate base. That was a buffer solution. Or if you have a weak base with its conjugate acid, that's a buffer solution. So buffer solutions have common ion effect going on in them, and these are usually the two ways you have a buffer. So buffer solutions resist change in pH even when there is a huge amount of acid or a base added. A buffer has a significant quantity of both HA, which is the acid, and its conjugate base, allowing it to shift in either direction when acid or base is added. So here's an example of buffer. So when an acid is added, the base part of the buffer reacts with the acid and neutralizes it. In the same way, when the base is added, the acid part of the buffer reacts with it and neutralizes it. So when you drink soda, which is acidic, your blood, which is a buffer, the basic part in the blood will react with the acid in the soda and neutralizes it, resulting that your pH of your blood doesn't change that much and it remains at 7.4. So here are 3 different combinations of acids and bases, and you're asked to find which is a buffer. So pause for a moment as you find the answer. So this is the answer. Only B was a weak acid and its conjugate base combination. The rest was strong acids and their conjugate base. So let's go ahead and calculate this question. Calculate the pH of a buffer containing an initial concentration of ammonia and then ammonium ion. And we are given Kb, which is the base ionization constant of ammonia. So whenever you have a buffer, you do buffer plus water gives you the products. So this is what you're going to have. It's very important that you know how to write the equation because that's the very first step. Then go ahead and look at the equation and see the amounts that you're given initially. So we have ammonia and we have ammonium ion. Then go ahead and do the change. So minus x plus x plus x. And then we already know the Kb, so we are going to go ahead and plug it in. So we get hydroxide as 2.7 times 10 raised to negative 5 molarity, and the pH we get is 9.43. So practice this question and see if you're getting the right answer. So part B is asking you calculate the pH of the same system as A, treating the initial concentrations at equilibrium concentrations. So if you remember, this is what we got initially, and then we do minus x plus x and all that. But now they're telling us just consider this to be your equilibrium concentration. So over here it's 0.21, 0.14. Don't worry about the x's or don't worry about the change. So let us see what happens when we do that. So if we go ahead and put the information we had initially, we are going to see that we end up having 9.43 as our pH. And if you see in the previous question, even though we did negative x and all those things, we still got the answer as 9.43. So what this shows is that weak acids or weak bases in buffers, they ionize very little due to presence of a common ion. Therefore, initial concentrations are a good approximation for the equilibrium concentrations. So in many cases, there's no need for an ice table. in pH calculations involving buffers. So in next section, we are going to see a shortcut method of doing this. So the common ion method to review is a phenomenon which ionization is suppressed when you have a common ion, and a buffer consists either of a weak acid and its conjugate base or a weak base and its conjugate acid, and they resist changes in pH. So let's look at section 17.2, where we will see Henderson Hasselbach equation, which is the shortcut equation that we can use to find pH of buffers without doing an ice table. So this is the Henderson Hasselbach equation, so you can write it down. It's an important equation. pH is equal to pKa plus log of base over acid. So this whole thing is in a bracket. So the next few slides are going to show how we came up with this equation. So if you had a weak acid plus water gives hydronium and conjugate base, this would be the Ka. Now if we were to rearrange it, so we got hydronium on one side, this is what we would get. And now hydronium, from hydronium we can get the pH, because pH of hydrogen is going to be, negative log of hydronium is going to be pH. So we can do that negative log of hydronium, so we have to also get log over here, negative log of Ka minus log of Ha over A. So if we rearrange it so that there is no negative over here, we are going to get pH is equal to pKa minus log of acid over its conjugate base. So that is how we get this equation, which is known as the Henderson Hasselbach equation. So in Henderson Hasselbach equation, the concentration of conjugate base over acid can be in terms of molarity or moles. Let's go ahead and solve these two questions using the Henderson Hasselbach equation. So we are given the concentration of the acid and its conjugate base. Again, acid and its conjugate base, and we are given the Ka. So this is the Henderson Hasselbach equation. We have Ka, we have to find the pKa, and then both of these are given to us. So that's just a matter of plugging numbers in, and we're going to get our answer as 3.59 for part A and 3.92 for part B. So try these questions out and see if you're getting the same answer. So some things to keep in mind when you see base and acid concentrations. If the acid and base concentrations are the same, so if it's 0.5 and this is 0.5, you're going to get log of 1, which is 0. So that means that your pH is equal to pKa. So that's what's given over here. So in the same way, it's showing us that if your base is greater than your acid, then this ratio is greater than 1, and you're going to find that your pH is going to be greater than pKa, because you'll end up having pKa minus a number. So your pH is going to be greater than pKa, and vice versa when the ratio of base over acid is less than 1. So this isn't something you have to memorize. You're going to see these trends as you do more and more of these buffer problems. So here's another example. Calculate the relative concentrations of acetate ion and acetic acid used to make a buffer solution with a pH of 4. Ka is given. So this is the Henderson Hasselbach equation. We have the pH, we have Ka, so we have to convert it to pKa, and we are asked what is the ratio, or what's the concentration of one in terms of the other. So we pretty much have to find this. So we have to get everything else on one side and this on the other side. So go ahead and pause the video and try that. So this is what you should get. If you put everything on one side, you're going to end up getting log of base, conjugate base over acid is negative 0.74, and just both of them is going to be 0.18. So the concentration of acetate must be 0.18 times the concentration of acetic acid. Now, what is buffer capacity? Now, suppose if I were to drink 1 can of soda, my buffer can probably neutralize it. The base part of my buffer reacts with the acid and it neutralizes it. But what if I keep on drinking like 10 gallons or 20 gallons of soda? We will get to a point where the buffer will not be able to counteract it. And at that time, I say, well, my buffer no longer can do this. It can no longer counteract all the acid that I'm drinking. So the effectiveness of a buffer solution is based on two factors, which is the buffer capacity and the effective pH range. Buffer capacity refers to the ability of the buffer to resist the change in pH, and it's dependent on the concentration of the acid and the conjugate base. So if acid and the conjugate base have a higher concentration, it means they will be able to counteract whatever is added to a higher degree. So buffers are most effective at pH values within 1 pH unit of the pKa of its conjugate acid. So here's an example. Calculate the pH of the following solutions: 0.150 mole of acetic acid and 0.195 mole of sodium acetate. As soon as you read the question, you should be able to recognize acetic acid is a weak acid, sodium acetate is a conjugate base of that weak acid. This is a buffer solution. So you can use Henderson Hasselbach equation to solve it instead of ice table. You can also use ice table, that is completely fine. It's just that ice table will take a longer time. So once you have found the solution to that question, question B is asking 0.0300 mole of solid sodium hydroxide is added to the buffer from part A with no change in volume. So what this means is that a base is added to the buffer. What is going to happen to the buffer? And part C is asking the same amount of sodium hydroxide is added to 1 liter of pure water. Now we know if you add it to pure water, the pH is going to change. But we expect that if you add it to a buffer, the pH change is not going to be that huge because buffers resist pH changes. So part A was simple enough. We recognized it's a buffer and we put it in the Henderson Hasselbach equation to get our pH as 4.86. Now for the second part where NaOH is added, we need an ice table. So let's go ahead and read the question again. We originally had 0.150 mole of acetic acid and 0.195 mole of sodium acetate. So when we write our equation, the first thing is the equation. Our buffer has both an acid part and it has a base part. In this particular case, we are adding sodium hydroxide. So we are going to have the sodium hydroxide react with the acid part of the buffer, which is why this reaction has acetic acid plus sodium hydroxide, and then we go ahead and see what products that we get. So this is really important. If you were having a buffer and you said an acid was added to the buffer, you're going to look at the base part of the buffer and add acid to that part. Okay. So this is why the very first thing is writing the equation and figuring out what the equation is. So read the question and spend some time figuring out what your equation should be for the ice table. So once you have done that, this question is saying 0.0300 mole of sodium hydroxide was added and the volume isn't changed. So this is important because if volume is changed, we have to change the molarity, but we're not changing the molarity. So we're going to have 0.0300 over here. Now this 0.0300 is actually reacting with the acid. So what we are going to do is over here we're going to have let me actually go ahead and write it down. So 0.0300, and over here also we have negative 0.030, and over here we have positive 0.030. So this sodium hydroxide is going to completely react with this. So we are going to end up having no sodium hydroxide. So in your textbook, you may even see it written as 0.0300 over here, and then it's negative over here, and that's how it is 0 over here. So you add a sodium hydroxide to the buffer and you expect the acid to react with it completely. So there is no more sodium hydroxide left. That is why it is 0 over here. If it is within the buffer capacity. Now it is possible that we could have added 1 mole of sodium hydroxide. In that case, we would have the buffer completely react with the sodium hydroxide and we would have sodium hydroxide left over. So that buffer would not have the capacity. But in this case, because it's 0.0300, we are going to do negative that from the amount of our acid, and we do have a positive number. We do positive over here because if we're subtracting on the reactant side, we're adding on the product side. So we do have numbers over here. So we're going to again plug it into our Henderson Hasselbach equation to get our answer as 5.02. Now, if you see previously, before sodium hydroxide was added, it was 4.86, and after sodium hydroxide is added, it's 5.02. So it's not too big of a difference. Now, our third option was when sodium hydroxide was added to pure water. So we have 0.03 moles of sodium hydroxide divided by 1 liter, so the molarity is the same, and we can find the pOH and then subtract it from 14. So the pH is 12.48. So when you add it to water versus when you add it to a buffer, we see a big difference, 12.48 versus 5.02. So we see how the buffer is able to resist the change in pH. So to review this, buffer capacity is the ability of a buffer solution to resist a change in pH when an acid or a base is added. So we were able to see the few different conditions where a buffer can be made and it's good at resisting pH changes. We saw the different combination, weak acid and a conjugate base, or a weak base and a conjugate acid. And then we also learned that Henderson Hasselbach is a shortcut method to find the pH for buffers. And with this, we end section 17.2.